explain how did you get this answer. There you have to write in very brief what how you got the answer or what is your logic. Most of the questions are numerical types, or they ask you to interpret programs and to write programs in MIPS assembly language. Okay. So they ask you that given this program, what is its meaning or what is its action? What does it do? This type of thing. And on the other hand, given say an equivalent C program, convert it to MIPS program, or given an operation for which C library function is already available, implement it in MIPS. Of course, we won't ask you to implement very difficult C library functions. Extremely easy, short things which can be implemented easily. You will see some examples in today, in future today or maybe tomorrow's class also. Okay, this type of things will be asked.
Sir, I had a question.
Yes.
So you said that we might get questions from digital design as well. So could the questions also include things like designing registers or flip-flops, or is it only limited to combinational circuits?
No, very simple combinational logic.
Okay.
Argument. I mean, tricky question. Like these are questions which you need. These are slightly tricky actually, but the answer or calculations are not very difficult. Okay.
All right, sir.
Of course, we will not give you complete FSM design that solve Carnot maps and do this, do that, implement this using this type of flip-flop, all those large things, because
okay, thank you, sir.
Given the nature of the online exams, those questions are very difficult to set.
Yes.
Those we will not give, but we will give you questions to check whether you have whether you understand Boolean functions and how to logically argue about them. Okay.
Okay, sir. Thank you.
Most of the questions you will find is based on your even the MIPS programming as problems. Some directly ask you to implement something in few like 4 or 5 instructions, 4 or 5 instructions maximum, maybe maximum probably there is one question that might require you to write maybe 6 or 7 instructions, but most of them are 2, 3. In fact, we mentioned in the questions that do not use more than 3 instructions. This type of thing. So they are very, very short code snippets you have to write, and the others are MIPS programs or code snippets which you ask you to analyze to see whether you understand and can visualize what an assembly language program does. Okay, yes, somebody was asking something. Yes.
Sir, can you please repeat the format of the submission, like how will
all detailed instructions will be given in the question paper. Follow the instructions and submit. Okay. Okay. This was the first announcement. Second announcement, in spite of repeatedly telling you in the last class, please do not email submissions. Many of you are emailed. It's currently it was kind of filling up my mailbox. So I have deleted all those emails, and I have opened the lab assignment till 5 PM today. That is the final extension. No further extension will be granted. Please go ahead and submit. I did not expect so many of you would have problems. I think at least I found at least 12 to 15 groups have emailed me the solutions. Okay, and each of those solutions in zip folders naturally are at least a few megabytes at least. Some of them are 10 megabytes or so. So I mean, don't do this. Okay, this just irritates me. See, we are responsible and sensitive enough that if you have problem in submitting, we'll extend the deadline. But don't do something which the teachers are repeatedly requesting you not to do. Okay, it will just irritates us. Nothing else happens. I will not forward it to the TA. Okay, there is the entire. utility of Moodle is that there will be a record of when people have submitted, what people have submitted. This type of divergent things, like somebody submits on Moodle, somebody emails to this teacher, somebody emails to that teacher. Some student, some group has emailed to Professor Bhargav Bhattacharya and he has forwarded to me. Why have you emailed to Professor Bhargav Bhattacharya? Is he involved in the lab? You are in third year, you don't have this minimum sense. This is only going to create confusion. What if he had missed this email and he had not forwarded to me? What would have happened? What is the entire concept? See, this Moodle is kind of a simple repository. Okay, of course, it doesn't have version control functionalities, but it is a repository of your solutions. What is the point of maintaining this type of repositories if you can just send? You can send through emails. I mean, email has existed for the last 30 years. You can always send by emails and we can forward to TA. What was the problem? The entire idea is to make things systematic and you are not cooperating. Again, I'm saying, please don't panic. Okay, you guys panic. Like I found 2 in the morning, 3 in the morning, you have sent emails. Submission deadline has passed. 3 in the morning, you're sending an email. The teacher will do something. What will teacher do? 3 in the morning. Don't panic. Don't get desperate. Anyways, we were discussing the set on conditional, this type of commands of instructions like SLT and SLTI. They work in an interesting way. Given a destination register, it sets it to the value 1, unsigned 1, or resets it to all bit 0, depending on whether the content of one register is smaller than the other or the content of one register is smaller than a constant. Of course, the constant as usual can be maximum 16 bits. So the SLTI instruction can only compare with 16-bit constants, whereas the SLT instruction can compare between two 32-bit numbers, one in register RS and the one in register RT. Okay, let me start the recording. I think I have not started recording. Oh, it has started. Okay. Good. Somebody has started the recording. Fine. Now, this can be used. This type of instructions can be used in combination with the branch instructions to implement operations like if content of one register is smaller than content of other register, go to L. This type of things can be implemented. How? You first collect the result of the comparison operation in another register, say in T0 in this case, and then you compare with register 0. Register 0 you already have available automatically, so nothing, you don't need to spend any further instruction to load the constant 0 anywhere, and you can directly compare with register 0 and then you can branch. The question is, why didn't we directly combine these two functionalities and have support for instructions like BLT, BJE, etc.? This is a very profound question. Okay. The reason is that, first of all, from your knowledge of digital logic that you have studied in the last semester, you know that comparator type hardware, smaller than, greater than, equal to, etc., they are slower than equal to or not equal to type of operators. The reason is that in equal to, not equal to type of operators, you can combine every bit pair in parallel and then finally combine the results of the comparison of individual bit pairs to give you the final result. But if you are comparing two 32-bit quantities, say for whether they are smaller than the one is smaller than the other or one is greater than equal to the other, etc., there is a dependency. Okay, you need to start from the LSB side, compare each other, and then go to the next bit, then go to the next bit, then go to the next bit, etc. So the hardware design becomes complicated. and the hardware of course becomes slow. Now if we had a single instruction, we could have of course built a hardware to support these two, make two things together into a single instruction, but then that instruction would have been slow. And remember that the slowest instruction hardware determines the operating frequency of your microprocessor. So if say there are 100 different instructions supported by the hardware of your microprocessor, 99 of them finish within execution period of 1 nanosecond, then you could have said, okay, I will have my clock frequency to be 1 gigahertz. But problem is, say one of them is so slow that it takes 2 nanoseconds to complete. In that case, you will say, oh, this, see, 99 of them completes in 1 nanosecond, but this takes 2 nanoseconds. So my clock frequency cannot be more than 50 gigahertz. Okay, sorry, half gigahertz, which is 500 megahertz. So that is very unfortunate that one slow instruction is making everything slow. So all other instructions get penalized. Okay, and your entire system, your entire microprocessor becomes slow. So this is not done. They have said, okay, fine, I will solve it within 2 clock cycles. I will take more time, 2 clock cycles to solve it. But most of the times the other instructions will not get adversely affected. So this is a very good design compromise so that your complete system does not get badly affected. Then this is a very important concept. There are SLT, like SLT and SLTI. There are two other instructions, SLTU and SLTUI. These SLTU and SLTUI interpret the register contents or the immediate operands to be unsigned quantities. Okay. So what happens is, if you look at the numbers given S0 and S1, if you consider 2's complement number system, S0 is a smaller number because S0 is basically the representation of -1 in 32 bits. Whereas S1 is the larger number because it is 1 plus 1 in 32 bits. So if you perform SLT on S0 and S1, then T0 register will be set. However, if you take the same S0 and S1 and execute SLTU on it, this time T0 will not be set, because this time T0 will interpret S0 and S1 to be unsigned quantities. It doesn't know about 2's complement, as if it does not know about 2's complement number system. And in that case, of course, S0 is a much larger number than S1 in the unsigned number system. Okay, because it is full of ones. And in the other case, when we are considering 2's complement, it has 1 on the left hand side, and full of ones means it is a very, it's more or less it's a 1 on the left hand side means guaranteed negative number, and then we can find out that it is -1. So SLTU is very useful in array bound checking. Please have a look at the book of how this is done. Now in MIPS assembly language programming, particular logical address space addressing convention is followed. The addresses at the lower end typically is reserved for the kernel. Okay, so these are not usable by the user programs. The logical address space towards the lower side. Why I am saying logical address space? Because whatever addresses you see, programmer see, or whatever pointer values the programmer see when you are writing C programs, they are all logical addresses. Okay, it is not possible to know physical addresses directly, because the entire address translation mechanism, when we study virtual addresses later in this course and later in your operating system course in the next semester, when you study in detail, more detail, you will find that the entire logical addressing mechanism is opaque to the programmer. Okay, this happens automatically in the background, managed by the operating system and certain other hardware, and we have no control over exactly where our data is getting placed. So when we are talking of addresses, those are essentially 32-bit logical addresses. First of all, after the portion that is reserved, typically towards the low end of the address space, you have the text data. We already know what is meant by, sorry, not, I shouldn't say text data, the text part of the program. We already know what is text. A text is basically your program that actual assembly language program, okay, instructions. So every assembly language program that you write will get an impression of this logical address. Everybody has his own stack, everybody has its own text segment, everybody has its own data segment, etc., etc. Everybody has its own heap, the portion of memory from which dynamic memory allocation is done. We will not consider instructions which perform dynamic memory allocation, but you can have a look at instructions like SBRK and other things to understand. I think those are covered in Hennessy-Patterson to understand how that is done. So now the question is, see, if one program is occupying that text segment where its own code is settled, how can the another program have exactly the same text segment with exactly the same addresses? Natural question. Well, the question is, they are being given an impression that each of them has access to exactly the same numerical address space, but that's a virtual or logical address space. That's not real. The operating system is giving an impression to every executable program that it has the entire computer at its own disposal with a flattened address space. First of all, the address, the way the memory is allocated actually in real computers is non-contiguous. Here we are being given an impression that it is contiguous. It is actually not. Okay, so then comes the portion which contains the static data. These are usually global variables, which are the static or other static variables in C. Global variable, constant arrays and strings. We have already seen constant arrays and strings, even statically allocated arrays, all of them occupy this portion. Then we have the dynamic data allocation from a portion of memory which is called the heap, which is used in system call in function calls like malloc in C or new in Java or C++. And then you have the stack. Very interestingly, the stack grows downwards. Okay, so you have to remember this. The growth of the stack is downwards. The growth of the dynamic data segment is upward. By growth, it means when you allocate more memory, it starts filling up towards the top. The stack starts filling up towards the bottom. So it's just a reverse picture of the way we are taught stack in data structures. Okay, in data structures, you have a top of stack, and the top of stack keeps moving upward as you keep on pushing more data onto the stack. Here exactly the reverse happens. There is a dedicated register called the stack pointer register $SP, which keeps pointing to the top of the stack. To push more, you move down the stack pointer. You decrement the stack pointer to find an empty location. That is the new top of stack, and then you push your data into there. You want to push another data, you further push down the stack pointer and push the, store the data there. So pushing data onto the stack happens in two phases in MIPS. First, you push down the stack pointer to wherever location you want it to push. and then you perform a SW instruction to store your content from a register to the current location pointed to by the stack pointer. Okay, good. We don't need to remember the GP global pointer in this course currently, but the SP register and the program counter is not a programmer usable register. It's an inbuilt register which contains the instruction or contains the address. Program counter or PC contains the address of the next instruction to be executed. Please remember this. Not the current instruction that is being executed. There is a misconception among students. The program counter contains the address of the next instruction which is going to be fetched and executed. Okay, please remember this. Why is this important? Repeatedly I am mentioning this. We will see maybe in tomorrow's class. What is the implication that the program counter actually stores the next instruction which is not yet been executed, this address, and not the current instructions address. Okay, there is an implication of this. Fine. Now let us move to probably the most complicated portion of this entire topic, which is procedure calling or function calling. The steps required in MIP to first of all, MIPS. What is a function? In the context of language programming, that you have to understand. See, a high-level programming language like C programming language has a concept called a function. Okay, and there are several rules that are obeyed. Function has a prototype. Function has input arguments, output values. It has a body. There are certain rules of what can be described inside function bodies. Okay, one function definition cannot contain another function definition. All these other things are there. And then you can call the function, get values from a function, etc. Unfortunately, in MIPS, there is no concept as such called there is no, the microprocessor actually does not care too much about a function. It does not understand the difference between code written outside a function and code written inside a function. To the microprocessor, everything is a flat body of code. There is no hierarchy. In C programming language, functions can call other functions, that function can call other functions, etc., arbitrarily. Okay, arbitrarily deep you can go inside a nested function call. MIPS programming, we will see, supports these concepts, but the support is not very, what should I say? Support is not very explicit. The programmer needs to take the trouble of arranging things so that these concepts of function calls, nested function calls, recursive function calls, etc., these concepts can be implemented. Okay, and it is quite cumbersome and painful actually to keep so many things in mind, especially when you are writing complicated recursive functions, as you will see very soon. And you will appreciate that how the compiler makes our task easy by managing all of these things internally, automatically. Okay, so that is something that which is really we will need to appreciate then, but you must understand internally what is going on. Okay, So what are the steps required? To place the parameters in the registers, transfer the control to a procedure, you acquire a storage for a procedure. Okay, you perform the procedure's operations, place result in register for the caller to pick up and return to the place of call. All these steps you don't need to memorize. As we see functions, you will understand. What are the register usage conventions? Now again, you will need to remember this. Among these registers, the convention, again, these are conventions. These are conventions followed by assembly language programmers. These are not conventions imposed by the hardware as such. You can use, for example, the A0 to A3. These 4 registers usually are used. Register numbers 4 to 7. That is $4 to $7. These are usually used to pass arguments to a function. But it does not mean that you cannot use A0 to A3 for your ordinary calculations, not inside a function call. Absolutely you can use, but people try not to use, and people try to stick to the convention so that later, if somebody reads your code, who also knows the convention, later if somebody reads your code, they can debug it easily and understand your code easily. So please, it is requested you stick by the convention. Okay. Typically for the A registers are used as argument registers to pass on arguments to the functions. Maximum 4. If you need to pass on more arguments, you need to use the stack. However, probably we will not need to deal with that case in the examples that we'll show. V0 and V1 are 2 registers which are actually register numbers 2 and 3, $2 and $3, which are typically used to return values. What is meant by returning values? The procedure just calculates the final value and puts them in either V0 or V1, or maybe some other register. V0 or V1, or maybe both, and returns to the calling function with the expectation that the calling function will then pick it up from V0 or V1. So the calling function must know in which of these 2 registers the final calculated value has been put. Maybe it can be put in both the registers. Okay, so you can basically return 1 scalar value of 32 bits or 2 scalar values of 32 bits through this mechanism. Okay, then T0 to T9 are these 10 registers are the temporary registers, can be overwritten by calling. What is overwritten by calling? The function that you have called, there is no concept of local variable in MIPS. Okay, the register resource, the register file is common to both the caller function as well as the function that is called. The function that is being called is called the calling function. Okay, so these are common to both. That view is global. So that you will face that, well, there is no concept of as such any local variable. How is the concept artificially implemented? It is artificially implemented that, okay, the T0 to T9, these 10 registers, the caller function can do anything with them. They did not bother what was their contents earlier, because the calling function, sorry, it does not care what was there earlier, because the caller function also does not care what happens to these 10 registers, because it doesn't place anything valuable in these registers and then calls a function, because it knows that those register contents might be destroyed. How does it know? Convention. The program has been written in a way such that that is the inherent logic. Again, S0 to S7, these 8 registers are called callee saved registers. What is callee saved registers? The convention is, again, the convention is that the called function, if it is forced to use this S0 to S7, any of these 8 registers, it first saves the existing value of this register onto memory. then works on it, modifies whatever it does. At the end, it says, oh, now I must leave this register to the state in which it was when I received this. Okay. So it restores the content of that register from memory, and then it knows that, okay, I have kept its original content back. Now everything is fine, because the caller expects that these 8 registers contents will be identical to when it called the function and another function, and when that function returned to it. These contents should not change. Again, it's a convention. The hardware does not force anything. It's the programmer imposed convention that keeps everything in order. The hardware is not going to stop you if you destroy the contents of the S0 to S7 registers. Nobody is going to stop you. You can do it. Because to the hardware, a function call and caller function, callee function, everything is kind of the same. It doesn't care. Okay. Global pointer, we don't need. Stack pointer contains points to the current location of the top of the stack. We have already mentioned this. And frame pointer we won't need. Return address, well, return address is the address to which you have to return. This is a very, very important piece of information. Okay. This information, why is it important? Because your function calls, as we will see very soon, it just jumps. It is basically a jump to a new location where your function has been defined. Okay. Now you need to return back, right? Typically, you when you are executing loops, you go back to some earlier location. Again, you come to the end of the loop. Again, you go back, or you just go to the next instruction. Here, function calls are not like that. Functions bodies might be located far away from the current location. So suddenly you go to jump to that sort of a location. You need to remember where to come back. The return address or array register contains exactly this address. Fortunately, you don't need to store the return address explicitly into the $array register. Most of the times. Sometimes you do. We will see when we need and when we not need. There are special instructions available for correct return address value to the $array register. $array is register number 31. So we will primarily play with the A registers, B registers, T registers, S registers very rarely if we are at all deciding to use them. Try to avoid using them. If you are forced to use them, then what to do? You have to use them, and you have to follow the procedure of saving and restoring. SP and RA. These are the registers that we should be primarily concerned with. Now, although the MIPS processor hardware does not care about what is a function in general, it does have basic rudimentary support for function calls and returning for functions. It has support through 2 instructions. One is called JAL, jump and link. Okay. The JAL instruction, as such, the syntax is very simple. JAL function name. Okay, function name is just another label with a colon, like we have seen. Okay, but the JAL is a very is an extraordinary instruction. It is not like the ordinary J instruction, because it automatically puts the address of the following instruction in $array. What is following? Following is not the procedure to which it is jumping. Following is the is basically the address of the next instruction in the caller function, where it should come back after the function call is done, where the function so-called it should return that address. Automatically it just keeps in $array before jumping. Okay, please remember address to which control should come back in $array and then jumps. And finally, at the end of the procedure, there is another instruction called JR$array or jump register. This first copies $array to the program counter. Why program counter? Because program counter is the internal register which contains the address of the next instruction to be executed, right? So it copies that $array to program counter, and then in the next clock cycle automatically control returns to that because the program counter fetches that instruction from that location and executes, which means that automatically your control goes back there. It can be used for case switch statements, but we will not see them. So let us see some simple examples today. Tomorrow we will dive deep into this. First is a leaf procedure example. Leaf procedure means there is no nested function call. The procedure does not call any further procedure. Okay. So say the leaf example is say it takes 4 arguments g, h, i, j. It calculates f equal to g plus h minus i plus j and returns f. We have seen this code body earlier when we were studying MIPS at the beginning of our discussions, but this time it will be through something called like a procedure. Okay. So suppose the arguments g, h, i, j input arguments are in registers A0 to A3, and it is decided that f will be calculated using register S0. Now you can say why? This is a very simple procedure body. There was no need to involve S0 here. We could have peacefully lived with the T register. There are 10 T registers, sufficient. This is a very simple program. Yes, but just to show you what happens if you use a S register in the called function, they have decided that the F calculation will be done using the S register. And because you are going to do the F calculation using the S register, you must save S register on the stack and finally restore its value. Okay, that is the convention you must follow. And finally, interestingly, S register value is not returned to the caller because that is not the convention. Value would finally be returned through V0 only. So the V0 register will contain the final F value, which the caller function will pick up from somewhere. So again, the content of S0 has to be copied in V0. Let's see this. First, so leaf example, this entire procedure body starts with a label with a colon as usual and ends with a JR instruction. So the identifier for a procedure body, what is a procedure? A procedure body is a block of code which starts with a text label and ends with a JR instruction. So firstly, they have decided to make a gravely foolish choice of trying to use S0. So S0 has to be stored on the stack. How do I store it? Well, the current stack location is pointed to by SP and the stack will grow downwards. One register is 4 bytes, right? So I add -4 with stack register to push it down to point to an empty location. then I push S0 on the stack. There is no instruction called push. So of course I use the SW instruction to whatever is the content, current content of S0, I just store it on the stack with an offset 0 in the SW instruction. Why offset 0? Because SP is currently pointing to an empty location. And now that has been filled up by the old content of S0. Fine. Now it starts the board. A0 and A1, which is I and J, is added to T0. A2 and A3, which is whatever. Sorry, G and H is added to T0. IJ is added to T1, and A0 is used by subtracting T0 and T1. There was no absolutely don't. We could just $T0, $T0, $T1 peacefully. That would have worked, but anyways, this is their choice. Fine. So S0 contains the final result, but that result won't be returned. It must contain. It must be contained in $V0. So I copy it to $V0 using the add instruction with $0 as the second register. Fine. About this, you could have also used the pseudo instruction move $V0 $S0. That performs exactly this. That would have also worked. Fine. So S0's work is done. Now that S0's work has been done, it must be restored to its old value. How do I restore it? I just perform an LW instruction, copy its old value that was on stack back to itself, to S0, and then I adjust the stack pointer. The stack's work is done. So the stack pointer can move back to its old location. How do I move back? I move back. Basically, this is the pop operation happening. Strangely, the pop operation in a data structure basically makes the stack pointer go down. Here it makes the stack pointer go up because stacks grow downward. So I add 4 with $SP, restore it back to its old thing, and I perform JR $array with the confidence that the procedure which called leaf example, okay, so the leaf example was called somewhere, say from main or somewhere using this. This was a call for leaf, okay, leaf example. Now, if the next instruction, exactly the instruction after JAL was something, have the context that the JR instruction will bring me back exactly to the instruction which was in JAL in the calling function. Okay, the calling function has not been shown here. Maybe it is the main function. It has not been shown, but it is guaranteed that when JAL happened, that the address of that instruction was stored in $array, and the JR will make me go back to that location. Any question about this, students? Anybody has any question? Because this is slightly peculiar. Hello, are you there?
Yes, sir. Yes, sir.
So yeah, so no question. Now let us move to the next non-leaf procedure example. I'll see. Yeah. Oh, okay. This is the factorial function. I do not want to start discussing the factorial function right now. Let me just describe the general issues of non-leaf procedure. A non-leaf procedure is a procedure which can call further functions. Okay. So these are nested function calls. Now here it becomes slightly tricky. The question is, what is your return address? Okay. When function f1 is calling function, so when main calls f1, The return address is the address of some instruction inside, like we saw with leaf underscore example. No problem. But when F1 further calls F2, in that context, the return address is the address of an instruction inside F1, not inside main, because the parent function for F1 is main, but the parent function of F2 is F1. So what I have to do is, well, I have to store the old value of $array somewhere into memory, because the JAL instruction, if I call from inside F1, it is going to overwrite $array with the address of its next instruction. But the next instruction is the instruction inside F1. What will happen to the instruction in main? Right? That cannot be overwritten. That's a very valuable piece of information. Otherwise, I will, after the end of F1 and F2, where to return. From F2, say I return to F1, fine. But from F1, where to return? I don't know. I've lost my return address. That is dangerous, right? That cannot be allowed to happen. So the original return address must be stored somewhere. Okay. There is only dollar. Unfortunately, there is only $1 array register. There aren't multiple $array registers that you can store one return address here, the next return address there, etc. However, you have lots of memory space in the stack. So why don't we perform the same convention, and any register that has to be saved, I will save on the stack. That is my convention, and that exactly the same thing I have followed for S0 registers. I will now also follow for the array register. Okay, and my stack will keep on increasing if there are further and further and further nested function calls, because every time I need to save at least the return address that is guaranteed, and also maybe some other arguments and registers onto the stack. That's why you might have heard that the stack keeps on increasing as you perform nested deep function calls, and the stack operations take additional instructions. That's why recursive function implementations are typically often slow if there is a deep recursive call. The classic example that we will study is the factorial function using recursion. You know from your previous courses that factorial function in iterative manner is much faster compared to a factorial function call using a recursive manner. There are other examples of recursive function calls given in the textbook and in the combined SPIM, that manual. There is a function call deeply recursive function calls. I think Fibonacci might be there. And there is also something called a TAC, which is a pathologically deep recursive function call. So have a look at those. This is the. Do you have some time, students? It will take 10 minutes to discuss. Do you want me to continue of this factorial function, or do you want me to do in tomorrow's class? Hello? Hello, students, are you there? Huh?
Tomorrow's class, like we have another class.
You have another class now. You have classes at 2 o'clock, right?
Yes, that's what I'm saying.
Yeah, let me continue with this. Okay, it will take 10 minutes, but this is a very nice function. Let me cover this. Nothing to explain about the C function call. All of you know this. The logic is the first if clause. Well, somebody might argue that this is not perfect. What about if somebody passes a negative argument, because you are allowing both signed and unsigned integers. Let's not go into those discussions. I assume that either 0 might be passed. I mean, non-negative arguments will be passed. That is guaranteed. Maybe some before this function call is performed, some other sanity checking steps have happened. We have eliminated, which will eliminate and filter out non-negative, non-positive, or less than 0, like negative argument. So that possibility cannot happen. So its logic is quite simple. Everybody knows this. If it is 1, it returns 1. If it is less than 1, it returns 1. You could have written maybe less than equal to 1, but here they go down up to 1. And otherwise, it returns n into factorial n minus 1. Now, the decision is that argument n will be passed to register A0, and the result calculated will be returned back in register V0. This is, think about it from a MIPS programming perspective for some time. Your argument is in register A0. What does this mean? In the first function call, say from main, you call JAL fact. Yes, it is in A0. Suppose somebody has passed an argument 10. So $A0 has 10, and when it calls fact for the first time. But when the fact is called for the second time, it is going to use exactly the same argument register A0. Okay. But what happens to the first argument? The first argument, so will it be lost? Will it be overwritten by the new argument? That cannot be allowed to happen. So the argument of the original function call have to be saved on stack. The original A0 value has to be saved on stack before you call the function calls itself with the new value in A0. But then when fact 9 is called, it needs to call fact 8. But fact 8 will A0 will now have 8. What will happen to 9? 9 has to be saved on the stack, means A0 has to be saved on the stack. So along with return addresses, your A0 register values also have to be saved on the stack. Now it has not yet been shown whether this function uses any saved register, S registers. If those are used, those also have to be stacked. Let us check. No, luckily this does not use any S register. So saving S register is, that headache is gone. But two things must be saved in every call to the function. One is the return address and the other is the current argument value. We will go through this procedure instruction by instruction, line by line. If you do not understand, you ask me question, and after the class also, I'm sure based on my experience in previous years, students have confusion about the exactly what is happening here. But please go through it slowly, study this piece of code, see more examples in the combined SPIM document, and maybe your text also, and your ideas will be clear. So on the, I need 8 bytes because each report I seconded by 8 locations. Okay. I subtract 8 from stack pointer. The top level call is JAL fact. Okay. So inside fact, I adjust the stack for 2 items. I save, and now that I have adjusted the stack from 2 items, 2 vacant spaces have been created. You could have also done it -4 in 2 steps, but then your one additional instruction would have been required. Now 2 vacant locations have been created on the stack. That is not the way classically stacks operate, but here we are doing it just for the sake of efficiency. The stack pointer has kind of suddenly moved away 2 positions and created 2 vacant spaces. In the first vacant space, towards the top side, remember stack grows downwards. So towards the top side is inside the stack by 1 element. Okay. In the first location, I store my return address. That's a very valuable information. I will need it later on to return to the correct position. And at the current location pointed to by the stack pointer, I store my current argument A0. Any question up to these first 3 instructions, students? This should not be very difficult to understand. Now I perform test. Is my argument smaller than 1? I am just following the C code that has been given. Okay, exactly same. I use the SLTI instruction. The SLTI instruction will compare the content of A0 with the constant 1. And if it is true, it sets $T0 to 1. If it is true, which means SLTI handles the case when A0 is 0. Okay. Now, if T0 is 0, it means no, it is not smaller than 1. It is greater than equal to 1. So I need to do further work. So I compare $T0 with $0. If they are equal, which means nothing has happened to T0. Nothing has happened means it has been reset, means the comparison has failed. Because the comparison has failed, I know my argument is greater than equal to 1 and I need to do further work. So if not, I will go to L1. What is L1? We will see later. But if it is actually less than 1, in that case, I have my answer and the answer is 1. I don't have to do anything. I just load V0 with 1. I could have also written li $V0, 1. That would have also worked using the pseudo instruction li. Otherwise, you do it properly. Add I $V0, $0, 1. So that stores 1 in V0. My result is done. I don't need to do anything with the stack pointer. I have done. So I pop 2 items stack, bring back the previous location, and I perform a JR instruction. Okay, and my result is in V0. Now this JR $array in this instruction is the most complicated instruction of this entire code because it plays a dual role. The first role is that if your factorial had been called with the argument $is from main with the argument in A0, that time itself, the first time JAL fact is being called, your argument is 0. That case, exactly what I just now spoke, it will enter the function only once. It will see the terminating condition has been met and it will return to main through JR $array. Very easy to understand. It becomes essentially it becomes a leaf procedure because you had passed it the such an argument that there is no recursive function call required. The problem is most of the times that won't happen. You will get an argument which is 1 or larger. If that is the case, then recursion starts playing, and then $array does not return to your main function. It most of the times it returns to the function called recursive function called parent that called this instance of the current function. Okay, it returns just to the parent. That parent need not be the main. Probably it is not the main. It only returns to main once at the end. But till then, $array is not the return address in main. It is the return address in the parent function. Firstly. Secondly, result in $V0. What is result in $V0? V0 might not have the final result yet when you are making one return to the parent function, because that parent function also needs to further return to its caller function. That might need to further return to its caller function, etc., to calculate final value in V0. So that is not the. So this $array return works either in cases it returns to main when the first call to fact is with argument 0, or it returns to the parent caller function when an argument 0 has been passed in a recursive call, not in other cases. Now let us consider the other case. Now there was this case PQ $T0 $0 L1. Okay, so this is the situation where the argument is 1 or larger. The interesting cases of the recursion. What is L1? It goes here. L1's logic is just call the next function, multiply it with the current argument and call the next function. Multiplying it by the current argument will happen later. Firstly, it just decrements the argument and calls the next function. Okay, makes the next recursive function call. So it decrements the argument by 1 to essentially calculate n-1 in A0, and then again performs jalfact. Jalfact again, this jalfact basically takes it to itself. Again it performs, saves the argument, but this time this $array is basically the instruction of the address of the instruction following this, which is kind of here. Okay, and it saves the current argument. Again it goes through those same steps. Okay, and again it performs a recursive function call. In this way it continues. Now at some stage it reaches an argument 0. In that case, its $array is not the main function $array. Okay, its $array is the return address which is just after the address from which this fact was called, which is this. Okay, so with 1 in V0, it reaches this position. Okay, so it restores the original n that was just now pushed on the stack, and it restores the return address that was recently. All these are the recent address things pushed on the stack. Those are restored, and it adjusts the stack pointer to take into consideration that 2 items have been popped, and then it multiplies $0 with $is. How is it? And storing overwriting V0 with it. Mul is an instruction which multiplies 2 registers, A0 and V0, and stores it in V0. How is it doing it? What value is there in V0? Well, if you look at the C function call, if n minus 1 had become 0, okay, and 1 had returned, the current value of n is 1. So 1 will be multiplied by 1 and V0 will contain this. And then again it calls J0, JR. But what is JR? JR is not the final result, okay? It again returns to this position from where fact was called. Okay, again it restores the arguments. Now the arguments after call to 1, the arguments are probably 2. So 2 gets multiplied with the current content of V0, and again it returns to the return address. In this way, it unrolls the recursion. But repeatedly stuff that was pushed in the stack, last in first out order, was popped for the first time initially. And how the recursion unrolls by contributing these factors in to the multiplication in every return call. The first return call is the base condition that has contributed 1. Then it contributes 1 again. Then it contributes 2. Then it contributes 3, etc., etc. If say it was contribute up to 10, and finally when all recursive function calls are exhausted and the stack has been completely popped out, it finally performs another JRA to return. That is the final return address that was stored first time when it was called with an argument made 10. Okay. So the complexity of the code arises from the fact that it can make returns to the caller function, either the main function or the parent caller function, from 2 separate locations. One location is this $array location, which handles the situation when the effective argument value has decreased to 0. And the second one is this location when the argument value is non-zero. From both of these locations, it can return either to main or to the parent function call. Okay, that is the complication of this function. You may try to implement it in some other way, absolutely fine. I mean, it will be still recursive, but maybe in some other way you can try to implement, no problem. Okay, I encourage you to do it. But do you understand this, students? Please, as an exercise, and this will be required because you will from now. As an exercise, carry out by hand the entire execution flow for small argument, say 5. So $A0 contains 5. Say this is the case, and then figure out number the instructions from 1, 2, 3, 4, 5, 6. How many instructions are there? 9, 10, 11, 12, 13, 14. There are only 15 instructions. Number the instructions from 1 to 15, and on use pencil and paper, just figure out this 15 instruction code. Okay, and this code works perfectly. To current are restore current as well, and reading to locations either to main or to the caller function. Hello.
Yes, sir.
Yes, sir. So please work it out by hand, okay? Once you get the hang of this program, all other programs, non-recursive programs will seem very easy. Okay, this is a simple program. It's not a difficult program, just that because it is a recursive program, it looks a little difficult. Now think about the Fibonacci implementation in MIPS. The problem with the Fibonacci recursive implementation in MIPS is that it needs to make two recursive function calls. So the fun will become double, okay? So I think it is there in the textbook. Please have a look at it. First you analyze this. First you make sure you understand this single recursive call program. Then you have a look at Fibonacci and then maybe if you can try to have a look at this. Wait. So now you understand how much work goes on behind the scene to make function calls and recursive function calls possible. I'm not finding the tag function call. Maybe it's there in the textbook, not in the manual. So there is a tag function call. Yeah, so this is the tag function call basically. This is the definition of the tag function. This is a pathologically a complicated recursion intentionally figured out to check how good your stack mechanism is. This can be used actually to check your load store and stack pointer, how efficient it is in the hardware implementation. Okay, so this has been used as a benchmark for optimizing recursion and support for recursion in a particular language or in a particular hardware architecture. Okay, so there is a triple recursion and everything is enclosed within another level of recursion. So it is mind-bogglingly complicated essentially. But people have also implemented this in MIPS, and you can also try without looking at the solution. Okay, thanks. We'll meet tomorrow to discuss further functions. Manipulation of string type of characters. We have already seen one program. We will see some more. Manipulation of strings and calculation of addresses. Thank you.